Any questions, or you want to check back and then ask me next week? Or you want to ask now? Or any questions you want to ask now?
Teacher, after class, I ask can.
Okay. No problem. Okay, so we look at this one first. Actually, Chloe, I want to ask you, right, because you are the one that joined from the first class, right? And I'm not sure how's your maths basics and things like that, because so far we have been doing, at least last week, we have been doing a lot of the graph stuff, right? Do you think, because I just want to know your opinion, do you think I'm going, if let's say 5 is a comfortable speed, 1 is very slow, and then 10 is very fast. Okay, this one is comfortable, just nice. This one is very slow. Where do you think I am now? Like, because right now there's only you, so I would want to follow your speed that you are comfortable at. If I'm a bit slow, then you can say like 3 or 4. Yeah, no, roughly at least. What do you think?
5.
5. Now it's just nice. Okay. All right. Not too fast, not too slow. Really just nice for you. you can be honest. I'm fine now, because I'll go at your speed now. Okay, can I? Right. So any question, as usual, you just ask. Okay, we continue first. Okay. So last week we were doing some graphs. Okay, last week we were doing some graphs, and we were not done yet in this question 2.6. And very sorry, I forgot to send you guys the notes earlier, the chapter 2 notes. So if you haven't print yet, it's okay lah. We won't touch on chapter 2 so much today. Okay, that is if we even touch lah. So we'll see whether or not we have time. So if you haven't print, it's okay. For next time I'll send earlier, because I'm not in a group with you guys, so I keep forgetting. Okay, let's look at question D. Question D. If y and x squared is drawn against each other, y against x squared in part D, for the graph of y equals to 6x squared, they ask us to state the relationship between y and x squared. Okay, so the graph that they draw is y against x squared, right? For us to imagine easier, I can draw y, and here is x squared. Okay, y and here's x squared. You see, the equation is y equals to 6x squared. Okay, y equals to 6x squared. Y is here already. X squared is here already. I think you should have learned in maths, right, that whenever you have an x squared graph, it would be a smiley face or a sad face. Right? You learned this in maths, right?
Yes.
Yeah, okay. Yeah, now you can just use your mic. There's only you. Okay, y and x. And then, but then that is the thing when we put x lah, then it will be a smiley or sad face. Okay, but then if I go and put x squared, then it will be a different story already. Okay, then it will be a different story already. You imagine this if I treat this as just a normal x, like just a normal x, am I right that 6 will be the gradient of this graph, right? If I treat this as a normal straight line, then 6 will just be the gradient, because I got y equals to mx plus c. There's no c here. Okay, there's no c. This x is what you put on your graph. This y is what you put on your graph, right? So 6 is actually just the gradient if I draw the graph of y and x squared. Okay, if I draw y and x squared, then whatever numbers here would be just a gradient. In other words, I want you to know that this actually will form a straight line if I put the x squared here. Okay, and it will pass through 0 because the y-intercept is 0. The gradient is 6. Okay, so for this case, right, the relationship between y and x squared, based on this graph, will be y is directly proportional to x squared. Okay, we want the relationship between y and x squared. Y is directly proportional to x squared. Later on, you will learn in your at Maths got one chapter in chapter 7. Yeah, in chapter 7, yes, 7. The chapter is called linear law, right? You will see that in that chapter, right, we can change the things that we put at the axis as different things. Like sometimes you can put x, sometimes you can put x squared, sometimes you can put x cubed, and so on, right? So if I change the thing, then usually, or most of the time, I change it to make it become a straight line, because straight line is easier to deal with. Straight line easier to read the values, and straight line can find gradient easily, straight line can find intercept easily. Okay, that's why we like straight line. Therefore, I go and put, instead of x and get a smiley face, I go and put x squared. Okay, so can you understand why 6 is the gradient? This one you can understand? For part D?
Is it because we ignore the x square?
Yeah, we just treat the x squared as the normal x.
Okay, understand.
Yeah, so this is like y and x. Imagine if I change this to y and x, then it will look the same. Okay, so the y and the x can be different things. Okay, so we look at part E. Now they want to find the relationship of y and square root x. Okay, the graph of y against square root x is drawn. Okay, the equation look like it's complicated because got the fraction there. But if you go and pull out the fraction, right, the 4/3 actually is just a number, right? Am I right that the square root x, I can write at the top, or I write at the side is the same one, these two? I write on top or write at the side is the same one, right? So again, we have the same situation. We have the same situation, y and x, y and x. Again, no y-intercept. Okay, no y-intercept, or the y-intercept will pass through 0. And then the gradient is 4/3. I know for sure this one will be confirmed a straight line again. Okay, because this one follow just y equals to something x like that. It's like a normal straight line. Okay, so I just want you to get used to the idea that if I change the x or change the y a bit, okay, as long as in the graph also I change, then it will be a straight line. This one also the same. Y is directly proportional to square root x. Okay, that is E. Then for F, let's look at this. For F, I got a graph of y against x. They ask you to find out the relationship of y against x. Okay, y against x, but the graph is like this, y equals to 5/x. Okay, y equals to 5/x. If you pull it out, the 5 and the over x like that, it will look like this. Okay, 1/x and a 5. Okay, for this case, right, whenever you have 5 and 1/x, it will form a graph that looks like this. Okay, it will form a graph that looks like this. This is what we call as y is inversely proportional to x. I teach you how to see. Okay, I teach you how to see. Whenever you have equation y, and then the x is at the bottom, this one is on top. This one at the bottom. One on top, one at the bottom, right? It will be inversely proportional. Okay, one on top, one at the bottom, it will be inversely proportional. So for this case, this is going to be y is inversely proportional to x. This is something new. This is something new. We didn't go through this before. Okay, but unless if I go and write the axis here as 1/x, then no problem. Why? Because this one is like the x, and then this one is like the y. Then the 5 is like a gradient, so it will form a straight line. But sadly, no lah. Okay, sadly, this is just asking you to draw that. So if you have x at the bottom, you must remember it will become inversely proportional. Okay, inversely proportional. And you imagine this, one at the top, one at the bottom means that if the y value go up, the x value will go down. Or the x value go up, the y value will go down. It will be opposite one. That's why we say it's inversely proportional. I don't know in MS whether you learn already or not, something called inverse function. Inverse function means the opposite function, right? That means one go up, one go down like that in the case of this. Okay, so last part is on G, where we do the graph of y and 1 over x. Okay, this one might be easier to understand. It's the same as D and E, this one, because you have y equals to 6 over 5x, right? You see your graph here is 1 over x. You can try to pull the 1 over x out and separate it from the 6 over 5. Okay, I hope you know that if x is on top, you pull it out, it will be like this. But if x is at the bottom, okay, so at the top and at the side is the same one. But if x is at the bottom, you cannot just pull the x and pull it to the side. It is wrong one, okay, because at the side means at the top. So if you pull it out, no problem. You have to leave it down there also. Okay, but takan on top, we don't write anything, right? We'll put a 1. Because 1 times 6 is still 6. I didn't change the question, you see? Then 5 times x is still 5x. Okay, so you need to know how to separate like this first. 6 over 5, 1 over x. Then it's the same thing as D and E. Remember, we got this on the graph and we got this on the graph. Again, no y-intercept. Okay, no y-intercept. And 6 over 5 is the gradient. It will form a straight line. This is what we call as y is directly proportional. So a lot of directly proportional. To 1 over x. Okay. Then let me know, or you got any question you ask me.
So for the 1 over x, can I also put x power of -1?
X power -1. Can. But they want the relationship between 1 over x. So you can just leave it as 1 over x. Most of the time, we'll just leave it as 1 over x. Oh, you mean you want to bring the x go up and then becomes x power -1? Yeah, that's fine. Like this one. Like this is the same meaning. This is correct. Okay, they're equal. Either one also can. Because you learn in Form 3, right? X power -1 means if you want to remove the negative, you put it at the bottom. Okay, put it at the bottom, you become +1 already. But on top, we don't leave it empty one. Okay, we must put a 1. Cannot put 0. 0 means the whole thing becomes 0 already. 0 over anything is 0. So must put 1. Okay. After you're done with this, right? Can I go up for a while back to that graph table? This one done?
Done.
Okay, we go back to the graph table for a while very quickly. I want to explain something. Okay, maybe right on your table here, okay, you can add on something. Okay, you can add on something. So for the shapes of the graph, when we have y is directly proportional to x, I just want to show you how the equation usually looks like. Okay, how the equation usually looks like. So we can write a few examples. Okay, you can write EG or EX to represent example. For example, we have y equals to 2x, or even y equals to x, or y equals to maybe 5 over 3x. Okay, you see that if you have y and x, and then you have some number, which is the gradient, it will all look like this. Okay, it will all look like this. So these are some examples of when it's possible directly proportional. Okay, of course, they can change this. They can change the x and the y value. Then let's say if they change the x or the y value, then here you change, then it's still directly proportional. Okay, but what is some examples for inversely proportional? Okay, a lot of people don't know this at the beginning, but inversely proportional just means those kind of graph, right? Where you have x at the bottom like that one. Okay, or just now we did something that looks maybe like 5 over x. Okay, as long as the y is on top, x at the bottom, this kind of graph is inversely proportional. Okay, and maybe you have, let's see if I do like 5 over 3x. Okay, it doesn't matter. So 5 over 3 is still a number as long as x is at the bottom. Okay, so I want you to see a very distinctive trend here. 1 over x, it is at the bottom. And there's a reason why when we draw the inverse graph, it looks like this. But then remember, just now we did a few graphs that if I go and change the x value, instead of x, I write 1 over x. For this kind of graph, I will make it become a straight line. Okay, because this one will become, okay, I write the 1 here to represent the gradient actually. Okay, I can put the 5 here to represent the gradient actually. Okay, I want you to see that actually, if I change this one as y and 1 over x, or y and 1 over x, y 1 over x, y 1 over x, it will definitely form a straight line. Okay, it will definitely form a straight line. That is why there are 2 ways to draw inversely proportional. Okay, one way is, both also you need to know. One way is we draw y and x, the normal one. Okay, you see x at the bottom, it will always look like this. It will never look like this or what one. It will always look like this. Okay, stick to the y and stick to the x. The next one is if I go and change the x. Just now we did a few practices already. If I go and change the x, then it will become just a straight line. Okay, this one can understand? These two directly and inversely proportional.
Teacher, if for the y is directly proportional to x, if got negative in front means the graph changed to y decrease linearly with x.
Correct. You are right. Directly proportional must go up and positive. Okay. Decreases linearly. Yeah, you're right. Okay. Very good. So y is independent of x. Let's look at some of the examples. This one. This one would be, for example, y equals to 5, y equals to 1 over 2, y equals to 3, y equals to negative 2. Okay, it will just be a horizontal line. All horizontal lines, y equals to some number, one, confirm. Okay, y increases linearly. That means you still have a straight line. Okay, you still have a straight line, but then you have the y-intercept. So, for example, okay, maybe you see I go and copy all these ones. Okay, and I go and paste here. Wait, okay, I erase this one first. Okay, I can paste here. And I go and add some y-intercept value. For example, +3. For example, -2. For example, -1, like that. Okay, positive gradient will still go up. That's why we say increase linearly. Okay, we use the word linear whenever it doesn't pass through 0, okay, or doesn't go up. So like decreases linearly, like what you say is correct. Okay, if we have something that goes down, like y equals to negative 2x, that is considered decreased linearly already. Or y equals to negative 5x plus 2, or y equals to negative 3x minus 7. Important thing is the gradient is negative. We already learned for all the curves and all the lines, if it slants, which way is positive, which way is negative. I like to think of the letter A lah. Here positive, here negative.
Teacher, I don't understand the y is independent of x.
Increase and decrease linearly, okay.
Okay, teacher.
Okay, so this one will test you on your whether you remember these things. Let's say I give you a coordinate, okay? This coordinate, I call it 2, 5. Okay, am I right? That means here is 2 and here is 5. Right? Let's say I give you another coordinate. This is 4, 5. Okay, that means here is 2, here is 4. Then the y coordinate is still 5. I give you one more. Let's say this one is 6, 5. Okay, that means here is 6, and then the y coordinate is still 5. Okay, do you notice something about the y coordinate? They're all 5. If I ask you, what is the equation of this horizontal line? Okay, this horizontal line. Because all lines are, I can write out the equation line. Any line, you can always write out the equation line. The name of this straight line, right? It will help you in your maths also if you know this. The name of this straight line is called y equals to 5. Why? Because it passed through y at the 5 there. Okay, it passed through y at the 5 there. And you notice all the y coordinate on this line will always be 5. Okay, that's why it's called y equals to 5. It's just like why you have your equation like this, and this is called y equals to 2x. Because you put in different x value, you always get different y values. So all straight lines will have their name, okay, their equation. All the horizontal lines, you will need this in your maths and at maths. All the horizontal line will always be y equals to something. Okay, y equals to something. Why? Because it will pass through the y-axis, cut the y-axis, very obvious one, and cut at whatever point would mean the equation already. Okay, so meaning, right, if you have this one, we are going out of physics a bit, that's a bit maths already, but since I'm here, let me just explain to you, since I teach PT3 maths also, and then and maths and maths also. So you see this one, all of it has an x value of 2, 1. Okay, I can prove to you. Let's say if the this point, let's say this is 2 and 3. Okay, that means the x coordinate is 2, the y coordinate is 3, let's say. You will notice that all of the x is 2 and cut the x-axis. What is the name of this line? It's called x equals to 2 because all of the x coordinate on this line will always be 2. Okay, so this is learning how to write the equation only. Okay, this is learning how to write the equation only. Okay, so you have the y equals mx plus c type. Actually, y equals mx plus c is the more difficult type, this kind. Okay, finding this kind of graph, this kind of equation. Now you also need to know how to name any horizontal line or any vertical line. Okay, vertical line will always pass through the x-axis. That's why it's always x equals to something, x equals to something, x equals to something. Do you know that the name of your y-axis is actually, the equation of your y-axis is actually called x equals to 0? And do you know that your name of your x-axis is actually y equals to 0? Because it's a horizontal line, it will cut the y-axis and cut at 0. Okay, cut at 0. Can I understand now?
Teacher means that when y change but x, no, when x change but y still constant value.
Y is still constant value, x change. Yeah, correct.
Okay, understand, teacher.
That means, you see, I increase the x value from 2 and then go to 4 and then go to 6. Am I right? The y value is still forever 5, 5, 5, 5. Correct now. That is why we say that the x is independent of the y. Okay, or the y is independent of x. That means what? That means there's no relationship one. I increase the x value. It's like you do an experiment. Sometimes you will do manipulated variable, right? This one you are familiar. You change some values. The result you get forever the same. Okay, therefore I can conclude that, oh, I think x and y, they are not related. Independent of each other. They are free of each other. Independent means merdeka, right? Free from each other. Okay, can I say?
Understand.
Okay, so it can be any value, can be any value. Got no x means it's horizontal line. Y equals something, y equals something, y equals something. Okay. And then non-linear, nothing much, to be honest. A possible equation would be like, I won't give you examples for this one, but anything that is not a straight line, like for example, x squared or square root graph or x cube graph. Okay, but they won't test you this kind of things. The most they will go is some straight lines only. Okay, to be honest, if you roughly know this, you already know a lot more than most of your friends, I feel, that go for any tuition or, and I feel that these kind of things are good for you in your maths as well, because in your maths, right, if you look at a straight line graph next time, you straight away will already know what is the gradient, as in the sign of the gradient, whether is it positive or negative. And you see whether to touch whatever y-intercept, you already know what is the c value, y equals mx plus c. Okay, it will help you a lot. Can. So we continue with this experiment, example 2.7. Okay. Last class, right, we learned about the 5 things that you can do whenever we analyze a graph. That one must remember how to state the relationship. Okay, so the directly proportional, inversely proportional, that one is the popular ones. Okay, then you have the increase, decrease linearly, that one also. Okay, other than that, actually not as popular. Okay, not as popular, but you know is good for you. Okay, you know it's good for you. Right? So must remember this kind of shape, directly proportional, this kind of shape, inversely proportional. You'll keep seeing these 2 graphs in physics. You'll keep seeing these 2. Okay, inversely proportional means the x is at the bottom one. Okay, here can have some number on top. This one, like that. Here can have some number. Here can have some number. Let's say k some number. Okay, these 2 graphs must know. Okay. So I've highlighted to you what is the most important graph. You can go and star it. Okay, and how to state the relationship. There's that law. Then how to find gradient. Usually I will take the height, the y distance over the x distance, and then see whether positive or negative. Right? Because in physics we don't go too in depth. Okay, in maths maybe you can use this formula. So okay. Okay, can. And then area under the graph. Area under the graph we also did already. So things like area of triangle, rectangle, trapezium are some of the common ones. Let's say you forget any of them, then of course it's a bit hard to find out the area, but triangle and square, of course, you know, rectangles, you know. Just trapezium, sometimes people will forget. Okay, but trapezium actually is a combination of different shapes, usually triangle and rectangle, like in this case. If you forget trapezium, you can still do area of triangle plus with area of rectangle. Okay, still possible. But I highly recommend you know all these 3, because you will need this in your maths also. And they are very, very popular shapes. Then we have things like interpolation. Okay, just a recap of last week's. Interpolation means we get the value from the graph that is already drawn. Inside of the graph. Inter means inside of the graph, within the graph. Extrapolation means we get the values from outside of the graph. Okay, we need to extend the graph and get the values from outside the graph. So there are these 5 things that we can do, okay, to analyze the graph. Okay, let's look at 2.7. The apparatus setup shown is used to carry out an experiment to investigate the relationship between force and the extension of a spring X. Okay, Daniel has obtained the result of the experiment as summarized in the table. So there are two things here that we are finding the relationship of. Number 1 is the force. Number 2 is the X value, which is the extension of the spring. If you are not sure what is the meaning of extension of the spring, you can look at the diagram. At first, your spring originally has a length of this much, initial length. And then if you go and hang a weight, which is the force, okay, which is the force, if you go and hang some weight, the spring will definitely become longer, okay, will extend. So how much your spring extend? This is called the extension. Okay, how much your spring extend? That is called the extension of the spring. That would be in cm for this case, right? So F is the weight that you put, right? So we look at the table for a while. You will notice that if I go and put a heavier weight, then the spring will extend more and more and more. Makes sense? Makes sense. I extend longer, then the extension of the spring also will be more. Okay. We look at part A. Plot the graph of F against X. Okay, they ask us to plot the graph of F against X. That means what? Meaning, on the graph paper, here will be F and here will be X, right? I'm not sure if this is the first time you plot graph in physics, but let's try and see how to do it, okay? So I got a graph paper here. I think if you print in black and white, it might be gray in color, so it's fine. We are going to put down our axis. Okay, so you need to draw this out. We do together. Okay, I'll use until the maximum of the graph lah. So here's 0, let's say. And then now, here would be the x just now we mentioned. Okay, the unit is what? The unit is in cm. So we follow the table. F against x. So F is on top here. This one is N, newtons. Okay, newtons. So like that first, and then after that we need to determine the scale of the axis, because they didn't tell me what scale to use. Okay, what scale to use. So you see, right, we have 0 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. That is for the that is for the force F against X. Okay, so what I'm going to do is on the F there, we see we got how many big boxes? We got 1, 2, 3, 4, 5, 6, 7, 7 big box in total. Okay. But we need to draw until a 4. Okay. That means we can do that means we can do maximum until here only 4. Which means here is 1, 2, 3, 4 like that. Yeah, 1, 2, 3, 4. Okay. That's all right. A bit small this graph. But maximum until 4. So 1, 2, 3, 4. Yeah, I cannot do 0 0.5, 0 0.5 also, because not enough space. And then for the extension of the spring until 5.6. 1, 2, 3, 4, 5, 6. Okay, this one we can do also 1, 1, 1, 1. 1, 2, 3, 4, 5, 6. Okay, maximum until 5.6. So I think to have a 6 is actually okay. Okay, up to 6 is good enough already. Then we will start to plot the points one by one. Be careful because this one is the y value of this is the y coordinate and this is the x coordinate. So don't get mixed up. We will go and find 0.7 on the x and plot it to 0.5. Okay, 0.7 on the x is here, and go and plot 0.5 like that. Okay, go and plot the graphs, the point one by one. You can try to do this yourself as well. Just be careful, this is all your x value and this is all your y value. Okay, x and y coordinate. Then 1.4 is 1. 1 point. 1.1, 1.2, 3, 4 now. Okay, so this is 1.4. You will stop at 1 here. Use cross when you plot the points. Do cross like me. Don't dot. Don't use dot. Okay, dot not so good because cannot see very clearly. We want a cross, very clear one. Okay, for all your science graph, it's better to use cross if you can. Then 2.1 is 1.5. 2.8 is 2. I know a lot of students are not very comfortable with drawing graph. That's from my experience teaching maths and MS, but that's why you take this chance to try yourself to go and plot. 3.5 is 2.5. 3.5 to 2.5. Then don't mix up the points also. 4.2 is 3. You do first. When you finish with drawing this graph and drawing the line, then you let me know. Okay.
Done, teacher.
Then we start to answer the other questions. So that was just part A. Part B, you see the space here, we can write the answer in the space here. Okay, plot is part A, plot graph. Part B, state the relationship between f and x. You will see that when I draw this graph, right, I purposely go and extend the line so that I will touch 0. Okay, so that I'll touch 0. It makes sense, right? Because I know this graph should touch 0 1. Why? Because what is the relationship between the two things that we are looking at? F and the x, right? Meaning of F is what? The force that we put or the weight that we put onto the spring. So you ask yourself, does it make sense that if I have 0 force, I didn't put any weight, there's no extension, there's 0 extension. Makes sense, right? I didn't put any weight, of course the spring won't extend. Okay, if the spring will extend, then something scary is happening, right? So it makes sense, okay? And I purposely extend like that to clearly see that it passed through 0, because to state the relationship, if it passed through 0 or if it doesn't pass through 0, it makes a huge difference, right? Pass through 0 is, we will say, F is directly proportional to X. Okay, in exam, can you use all this F and X symbol? If the question itself use F and also X, then okay, can. Okay, if the question, usually the question will use some symbols, okay, usually the question will use some symbols. But if the question didn't give you F, then you might write force. Force is directly proportional to extension of spring. Okay, so even in SPM, they use F and X, you just follow only. That is the relationship already. Part C, calculate the gradient of the graph, K. Okay, they're saying that the gradient of the graph, they call it, instead of gradient, usually we call M. They want to call this gradient as K. Okay, never mind, we just follow. Okay, we just follow. What you need to do, right, is to draw a triangle. You need to draw a triangle. Okay, in physics, they are very, very particular. You need to draw a triangle. So I'm gonna do, okay, using this blue color. Okay, and your triangle, right? Also, they are very strict about this, cannot be too small. Okay, the triangle that you draw cannot be too small. So you must use a triangle that is quite big, okay, at least more than 50% of your graph paper. Okay, best is about like 75% of the graph paper. Okay, you see your graph this big, right? Try to do as big as possible the triangle. Okay, minimum 4 box. Okay, minimum 4 box for your gradient. So let's try to draw out the triangle, and you see why I need a triangle. Maybe I just use the last point. Okay, maybe I just use the last point and the first point of the graph. Okay, I know a bit light, but I hope you can see the light blue color one. Okay, you draw already, right? And then you take your, okay, let's say if you don't want to use the point down there, right? Because it will erase your x-intercept. You can use this point also, can, no problem. Or it doesn't have to be a point on the, it doesn't have to be a point that you actually drew. Let's say you want to use this point up to here only. Can or not? Can also. Okay, and let's say you want to do up to like here. Cannot, can also. Okay, so really depends on you. As long as this triangle don't too small, then all right. Okay, don't too small, then all right. So maybe I just use, Okay, let's stick to 1. Let's just use this. Here to here. Here to here. Okay. Okay, let's just stick to this. This one we don't want. Okay, I think that is big enough already. After you draw already, right, you need to remember, just rub a bit to make it dotted. Don't have to be perfect. And then put a 90-degree there. Okay, put a right angle there. We are going to calculate what is the y distance, what is the x distance, and go and find out the gradient. Okay. I think a good way also, right, is maybe we, in this case, maybe we can state what is the coordinate also can. That might be easier for us. So the coordinate that you want to use here is actually 5, 3.6. Then here is actually 1, 0.7. Okay, let's say if you want to use the y2 minus y1 over x2 minus x1 for the gradient, also can. Want to try that? Since we never did that before. The formula is like this, right at the side. Okay, so you take a y value, 3.6, minus the other y value, 0.7, over. If you start with this point first, then at the bottom also you must start with that point, which is 5 minus 1. 3. Oh no, my one is 3.6. Oh.
Teacher, the table show 3.5 for teacher.
3. Because 3.5 is connected to 4.9. You see now, 3.5 is connected to 4.9. But I want to have 5, ma. I don't want 4.9. You don't have to use the point. See, I'm not using that point, you see now. 3.5. This point, yes, is 4.9, comma, 3.5. I'm not using that, right? I'm using this point.
Teacher, is that wrong if I use 4.9?
Can also 4.9 and 3.5. It's just that our value might be a bit different, which is fine. Okay, might be a bit different, but it's fine. So you calculate yours, okay, and I'll calculate mine, and then we compare our answers. See how much it differs. For mine, I got 0.725. As long as you got show properly or working, write down the coordinates. Maybe this one we use the gradient formula to show clearly. Maybe it's better. Then you should be able to get your gradient value. In this case, the question say use k, so we just follow and use k. For your value, you probably get like 0.718. Was that what you did? Let's stick to that. Okay, so you stick to your one, I stick to my one. Okay, no problem, no issues, don't worry. As long as your triangle big enough, remember that. Okay, usually we don't take like 4.9. There's some reason to that, so that when we divide out, the answer will be nicer a bit. Okay, when we divide, the answer will be nicer a bit. If you notice, my gap here is exactly 4. Okay, my gap here is exactly 4, but yours is 3.9. So when you divide 3.9, of course, the answer won't be so nice anymore. You have a longer decimal. Okay, but all that's just from experience. If you ask me whether the value is wrong, no, it's not wrong. It's still correct. They must still accept your answer. Okay, but B, the equation that relates f and x is f equals to kx, where k is the spring constant. Determine the value of k in SI unit. Oh, calculate the gradient k show. Oh, there's one more thing that we should do, which is to put down the units. Okay, to put down the units. So just now we did y value over x value. The y value is Newton. The x value down here is in cm. Okay, so it's Newton divided by cm. So Newton cm -1. This is the k value. In part D, right, they're actually asking for the same thing. Okay, they're actually asking for the same thing. So you just have to write k is equals to 0.725 Newton per cm. So your one is 0.718 Newton per cm. Okay, you know how I got the Newton per cm, right? The unit.
Yes.
Yeah, okay. So in a lot of your graph questions, or in school, maybe you have done an experiment before, I'm not too sure. You will notice that for experiment, if you need to draw a graph, usually, and you want to find out the gradient, you must always draw the triangle, okay? Because they will always say how you determine, show how you determine one. So this is also a bit related to your paper 3. Remember I say paper 3 is doing experiment, getting report and things like that. For that one, we usually will ask you to find out what is the gradient of the graph. So they'll ask you to get some data, draw the graph, and then from the graph, show how you get the gradient and also get the gradient. Okay, that's when you draw the triangle thingy, put down the 90-degree, okay, get the y distance, y minus y, get the x distance, which is x minus x, get the gradient. Okay, and it also makes sense that my gradient is a positive value because the line slants like that. This is positive. If the line slants this way, then it's negative. Okay. Next one, E. The area under the graph represents work done in stretching a spring. Okay, determine the work done needed to stretch the spring by 4 cm. Okay, determine the work done needed to stretch the spring by 4 cm. So you don't have to worry about this. They are telling me that the area of the under the graph represents work done in stretching a spring. Determine the work needed to stretch the spring by 4 cm. Okay, at first I stretched the spring by 1 cm only. Okay, 1 cm, let's say. Let me use a different color. Okay, 1 cm. I need to use this much. This is the amount of work that needs to be done. Okay. Work done is like energy, how much energy needed. If I need to stretch until here, okay, until 4 cm, how much energy do I need? This is the amount of energy. Okay, we need to find out the total area under this graph. Okay, let's try and see. So this is just a triangle. This is just a triangle. The length of the base is 4 cm. Okay, the length of the base is 4 cm. What is the height? This height here is 2.5. Okay, 2.5. Here's 2.5. Then 2.6, 2.7, then 2.8, 2.9. Am I right? It's between 2.8 and 2.9. Okay, between 2.8 and 2.9. If it's middle, then we take the middle. Okay, 2.85. Can you get the value of 2.85?
I got 2.9.
2.9. Okay, it depends on your graph lah. If your one really is at 2.9, then take 2.9. If it's in the middle, then you take the middle. Okay, it will be more accurate. So yeah, your one might be slightly different from mine. That's fine. Basically, we will just do half times base times height. Okay, I'm gonna do. They say the area is what? Work done. So we just write work done equals to triangle 1/2. The base is 4 cm. The height is, you write 2.9 if your one is 2.9. Mine is 2.85 in newtons. The reason why I write the units, right? You can choose not to write the units first, is so that later you can see what would be the units for our final answer here. It'll be Newton times cm. Okay, Newton cm. Rarely we write cm Newton. Okay, Newton cm. So this is the unit. My one is 5.7. Your one would probably be 5.8. Okay, just follow your graph. Okay, Ken, no problem.
Teacher, the cm don't have power of -1.
When is it -1? When it's at the bottom, correct? Just now the one got -1. Why? Because the y value that we use, 3.6 and 0.7, this one is Newton over cm. Different thing, right? One is divide by cm. One is multiply by the cm. Okay, when divide, then you have -1. When multiply, of course, don't need to write -1. Correct?
Understand, teacher.
Great. Okay, can, good. So let me write off this one. Area, you don't need to draw the triangle to me. Okay. And then after that, we look at the next part. Part F, determine the value of F when X is 2.5 cm. Okay, for F, if I have a value of X is 2.5, I go to the X axis there, the X cm there. Okay, we just have to do interpolation, right? This one is called interpolation. Okay, when it's 2.5, here, my value is right here lah. And I want to tell you something about graphs, right? You see, you got the big box. Each big box got 10 smaller boxes. Okay, let's say, right, you want to read some value, and let's say your value land at here in the middle. Okay, maybe here lah, land at the middle. Here is 1, and here is 1.1. If it lands at the middle, then it's 1.05. This is the maximum you can split a small box into only. You can maximum split a small box into half only. Okay, because some people may say, right, what if my point that I want to read the coordinate is not very high, not very close to there, the top one, not very close to the bottom also, maybe like 75% of it. Okay, then you have to make a decision whether you think that it's closer to the middle or closer to the top one. Okay, because maximum you can only split into half a small box. Okay, you cannot say like you want to take 3/4 of it like that, cannot. Okay, a small box maximum can split into half only. This applies to your maths, your maths, or your sciences, same. Okay, that's how much you can split your graph only. The box is already so small, maximum can split only by half. Okay, so my one is like this lah. Some people may argue and say that their graph may be closer to the middle. Then fair enough, no problem. You read the value that is in the middle. Okay, so my one I will follow. My graph looks like it's closer to this line. Okay, so I'm gonna follow. Yours might be slightly different, but won't be too far away. This one also I'm gonna put dotted. So everything on your graph you can use pencil. Okay, all the drawings in science and maths can use pencil. This is going to be 1.8. Okay, my one is 1.8. What about yours? When X is 2.5, same. Okay, good. So I will say my F is actually 1.8. Okay, 1.8. Don't forget that you need newtons. So when X is 2.5, sorry, X is 2.5, F is 1.8. Last part, predict the value of X when F is 5.0 newtons. Okay, 5.0 newtons, meaning is up here already. Okay, if I got extra graph paper, right, then okay lah, I can go and extend and find the value. This is called extrapolation. Okay, extrapolation. So if cannot not enough graph paper, then what we do? We can also use the equation that we found out earlier. Okay, we can use the equation. So to predict, right, we can use the equation. It was F is equals to, your one will be 0.718, okay, the K, X. My one will be F equals to 0.725X. Okay, you follow your own one. And now we're going to say that F is equals to 5. Okay, so I'm going to sub 5 into my F there and find the value of X. Okay, your one will be 0.718. So this one, the number just have to divide over. My X value, I get 6.89 on 6.89690. Okay, my X is equals to 6.90 cm. Okay, so equation very useful because I can just sub in the F or the X and then can find out the other one. So yours maybe 6.96. Okay, 6.96 cm. You can just leave it like that. Okay, and you follow your one, huh? 6.9896, sorry, 6.96. Okay, if got extra graph paper, I will go and just extend the graph. I think it's easier. Okay, and do extrapolation. Yeah, this one. So far, okay.
Can, teacher.
We continue. Okay, so this one is done already. Next part. This orange table is on scientific methods and a complete experimental report. Okay, the steps of scientific method. This one actually you learned last time in science, but I just put it in here so that it's easier for you to see. Don't need to memorize this. Don't need to memorize this. They won't ask this in SPM. Okay, they won't ask this in SPM. The steps of scientific method used to solve scientific problems are: number one, identify the problem. Okay, so one day you have a guy sitting below an apple tree. You probably have heard of this story before. His name is Newton. Okay, he sits at below an apple tree. This guy's name is Newton. So first he identified the problem, why the apple fall down, right? This is called a scientific problem, right? It's regarding gravity. Okay, so first he identified what's the problem, why the apple drop down, why the apple will drop to the ground, why won't fly to the top, why won't fly to the left or right like that. Okay, why must always drop to the ground. Then he made a hypothesis. Okay, a hypothesis is a smart guess. Maybe he think, oh, there's a force that pulls it down. Okay, maybe that's the guess. And then he control his variables. Maybe he do some experiment. Then he plan the experiment. Okay, he want to do experiment. He control some variables, fix something so that it doesn't affect the result. And then he plan the experiment. Then he conduct the experiment. After the experiment, you always get something called responding variable. That is to collect the data. Okay, all your result is the data. Then after that, he analyzed the data. One very important way we learn how to analyze the data is by using graphs. Okay, graphs. And after that, from the graph, maybe you can make some conclusion. Okay, or maybe from the data, I can make some conclusion, and then you can write a report. Okay, this is the steps to solve a scientific problem. And then you also have a complete experimental report, because when you write the report, you know what to include. Okay, so there's things like inference. Okay, later we will see what's the meaning of inference or how to write it. Hypothesis, aim, all this you see before since primary school. Variables, you have responding, you have fixed variable, you have manipulated variable, then apparatus and materials, list down what you will use or what did you use in the report. And then what are the procedures? What is the steps you take to do this report? What is the results? And then how you analyze the data and what is your conclusion? Okay, so this one, right, we are going to cover in the next example, 2.8. Okay, it is on the period of oscillation of a simple pendulum. Okay, in here, right, there is a complete experimental report. Okay, the first thing we talk about is the inference. Remember, point number one, inference. Okay, so the inference is, they ask us to complete the experimental report. The inference is like that. The period of oscillation of a simple pendulum depends on its length. Okay, if you want, you can highlight the word depends on. Usually for inference, they will use these words depends on. What depend on what? Okay, what depend on what? So from here, you will see that the situation that we are dealing with is the period of oscillation of a simple pendulum and the length. Okay, we got two variables here. What is the meaning of period of oscillation? Pendulum, you know is what, right? A string and then hang a ball at it. Okay, this is what is a pendulum. Okay, this is called a pendulum. And then period of oscillation is the time to complete one full swing. Okay, or one complete swing. The swing is called an oscillation. Swing and oscillation, same meaning. Okay, swing means oscillation. So you swing to the other side and come back. That is one complete swing. Okay, must swing and come back to the original place. That is one complete swing. So we are saying that the time it takes to swing and then come back depends on how long the pendulum is. If I have a longer string, obviously it will take longer to swing to the other side and then swing, come back, right? So that is my hypothesis. I'm making a smart guess. If I swing to the other side and then come back, it will take a longer time as compared to if I have a very short one. Okay, and I swing and swing, come back. You will see the distance it has to travel is a lot shorter suddenly because the length is short. So the time also will be faster, right? So the period, which is the time, will be shorter also. Okay, so we are saying that how long it takes to complete the period is the time. How long it takes to complete one swing is dependent on the length. Okay, it depends on the length. Then number two, we'll state the hypothesis, a smart guess. Just now we already say, we will say that the greater the length of the pendulum, the greater the period of oscillation. Usually we use words like greater, or if something is greater, something is smaller. Okay, or you can say like, if the length of the pendulum increases, the period of oscillation increases, also can. Okay, repeat, if the length of pendulum increases, the period of oscillation also increases. Okay, however you phrase it, I like to use the greater, that one. Then next is the aim. Aim always to investigate. So the words I highlight is usually some of the words that we like to use. Okay, investigate the relationship between who. Aim is the purpose. What is the purpose of this experiment? Experiment is to investigate what is the relationship between the length of the pendulum and the period of oscillation of the pendulum. Okay. So what do you think we are manipulating here? Okay, now we'll state the variables already. You must, there are a few blank space here and we're gonna fill in. What do you think we are trying to manipulate? And what do you think is the result that you will get? Do you think the length of pendulum is the manipulated variable or the responding variable?
Manipulated.
Yeah, manipulated variable. So we will write down the length of pendulum, comma L like that, okay? Which is basically this one now, because I'm looking for the relationship between two things, right? So one must be I manipulate, one must be I get as a result one. Okay, so R stands for the things that you get as a result. R stands for result. Okay, that is the period of oscillation of the pendulum, comma, they call it T. So we use the same letter and put T there. Okay, then after that, constant variable. Okay, constant variable. You write period of oscillation, comma T also can. Don't need of the pendulum also is fine now. Okay, Constant variable, you need to, is something that we fix, okay? The fixed variable is something that will affect the result one. You cannot say, I fix the temperature of the room like that. Okay, no, no relationship doesn't affect the experiment, okay? Or at least it doesn't directly affect the experiment. You need to put something that if you change it, right, it will affect the experiment, right? Okay, it will affect the results. The best one is to say the mass of the pendulum bob. Okay, the whole thing here, the string together with the ball is called a pendulum, a simple pendulum. The ball is actually called a pendulum bob. Okay, the whole thing is called pendulum, but the ball itself is called pendulum bob. Am I right that I cannot be using different mass of the pendulum bob? It must be fixed. If I keep changing it, then it will affect the period also. Okay, because heavier and lighter, it will take different time to swing one. Okay, I'm not interested in the mass, how the mass affect. I'm interested in the length and how it affects the period. Okay, so we don't want those things to affect our results. Okay, so constant variable or fixed variable is something that could potentially affect the results directly like that. Okay, then the next part is we state the apparatus and materials. Okay, all these things don't need to memorize. I just want to introduce to you how a report looks like. Okay, introduce to you how a report looks like. Don't need to memorize, but some things you like can highlight like how I did. Depends on is usually what the words that they use in inference. Sometimes they will use something affects something also. Okay, similar meaning things up. Hypothesis, like I said, they can use something increase, then something increase. That aim is usually to investigate something relationship between two things. Okay, but learning how to write variables is important, I feel. Okay, then apparatus. Again, this one don't need to memorize. So just see how they write it. Apparatus, we have the retort stand, a protractor, a pendulum bob, stopwatch, meter ruler, G-clamp. Okay, and then materials is 100 cm thread, the two small piece of plywood. Okay, we look at the apparatus setup, the diagram here. Okay, let's see why we need all these things. The retort stand is to let the pendulum bob hang. Okay, the protractor, later we see what is the use of this protractor. Okay, protractor is to measure angle one usually. Then we need a pendulum bob. Okay, then we need a stopwatch. Okay, I need to count how long it takes to do a complete swing. And then I need a meter ruler. Why? Because I need to measure how long is this length of pendulum. I want to change the length. Then I need a G-clamp. Why? A G-clamp to make it stable. Okay, I don't want the pendulum swing and then the whole retort stand also swing like that. Don't want. Okay, we want to make it stable. If your retort stand is stable enough, you can don't need the G-clamp also can. Okay, then we want a 100 cm thread. Okay, the thread would be part of your pendulum, hang to the pendulum bob. And then two small pieces of plywood. The plywood is up here to what's that word? To put the string in between the plywood. Okay, to securely hold the string in place. Okay, so that the string will not go up, go down like that. Okay, it will to securely hold the string. Okay, so that is a fixed length, so that our pendulum bob doesn't change length. The length of the pendulum doesn't change. Okay, the protractor, right, actually is to make sure that I don't swing the pendulum at different angles. Because am I right, if I release the pendulum bob at a very far distance, then of course it takes longer time to travel. Okay, so it might affect our results. Okay, we will take somewhat around a 10 degree angle, so don't want too big. So maybe I just put the protractor there and then agak see, okay less than 10 degree, and then I release. I don't want too big and I don't want too small. Okay, I want somewhere every angle about the same, because that might also affect my reading. Okay, so these are why we need all these apparatus and materials. There are sometimes when we can also just combine apparatus and materials together. Usually, if in your paper 3, Okay, they will tell you the apparatus and materials beforehand, like 2 weeks before your real practical exam. Okay, they'll give you the materials and apparatus, the list. And then from the list, right, you can agak-agak see what experiment is this already. Okay, you can agak-agak know, oh, this one is probably from what chapter, and then you can plan beforehand. You can do reading and study beforehand. Then when you do the time, it's easier for you. So for all your sciences, is like that. Okay, usually 2 weeks before. So don't worry about apparatus and materials given to you. Okay, number one, set up the apparatus as shown in the diagram. Now we are writing the procedure. Okay, so we draw a diagram to show you very clearly how it looks like. So we set up, and after that, we adjust the length of the pendulum, L, to 20 cm. Okay, then after that, we displace the pendulum. Displace meaning let go of the pendulum at an angle less than 10 degree from the vertical, 10 degree from the vertical line, and release. Okay, less than 10 degree from the vertical line and then release. This is the vertical line. And then after that, we measure and record the time taken to complete 20 oscillations. So I don't want to just let the pendulum go one time, come back, and then press the stopwatch again. Like that's not very accurate. I let it go for 20 full swings, 20 complete oscillations. Okay, and then only I stop my stopwatch. That would be more accurate lah, because you can divide by 20 so that there's less mistake, less error. Okay, then after that, we will repeat the step 4 again. That means we will release and measure one more time, and that one will be T2. Okay, so we are doing the experiment 2 times because we need to find out the average value. Okay, fair ma, you do one time, maybe you make a small mistake. Then you do another time, maybe the result is better. Okay, we'll average out so that the value is not just based on one time you do. Okay, it's based on 2 times. So better, usually we take average result. Then after that, we will calculate the period. Period, you must remember, is always the time for one. Okay, the time for one. Just now I already wrote the time for one oscillation. So after you get the time taken for 20 full swings, you must divide by 20 to know one full swing actually is how much. Okay, and we will also go and find out the t squared value. Okay, so let's say this procedure is given to you. You just have to follow only. Okay, you just have to follow. Then after that, repeat step number 2 to step number 6. Okay, repeat all the steps for the length of pendulum of 30 cm, 40 cm, 50 cm, 60 cm, 70 cm. Then record the date. Oh, this one is a typo. The data. Record the data in the table. Okay, not the date. So the table looks like this. This would be your results. You have different length of pendulum. Okay, different length of pendulum. This is the time taken for 20 oscillation. Okay, 20 full swings. You do one time the experiment, this is the result that you get. You do the second time the experiment, let's say this is the result that you get. Okay, of course, we cannot do this in class now. So I gave you some values, and can you go and find out the T average for all of it? Okay, so small t here represents the one for 20. Big T is the period. You see up here, big T is the period. Big T need to divide by 20. All the formula already given to you up here. Okay, you just have to follow. So we just have to take in your calculator, you just type 17.6 plus with 17.5, and then we divide by 2. Okay, all of it, right? Let's just leave it as 2 decimal place. Okay, 2 decimal place. When you find average, you can do 1 more decimal place is okay. Don't need to leave it as 1. 2 is good. Okay, you try to find out all the values for this average one. When you do until this one, you let me know. Okay, this 4.
Done.
So the values are 25.00, and then here is 27.95, 30.80, and then 33.15, right? Okay. Or we fix the same decimal to make it neat and tidy up for your scientific reports. Usually we leave like that, same. Then to find out the t value, we just have to divide all of this by 20. Okay, because small t represents for 20 complete oscillation. Big T is the period. Must remember period is always meaning for just one only. Okay, just for one, the time taken for one. So it's still in seconds, if you see the units. So you just take 17.55, you divide by 20, you will get 0.8775. Okay, I'll just write all four decimals. Okay, I'll just write all four decimals. And for this one, maybe I standardize, put everyone as 4. Okay, that's okay. So I'm going to put 22.15 and divide by 20 also. 1.1075. Can you do for this two? And then maybe I do now for the bottom two. Okay, you do the for 40 cm and 50 cm. I do for 60 cm and 70 cm. You got the two already? You can get?
One 1.3975, and the next one is 1.54.
Yeah, 1.3975, 1.5400. Okay. Then all of the values, I'm going to square it. Okay, all of the values, I'm going to square it. But I want you to only round it off to 2 decimal place for this one. Okay, later I'll tell you why, but can you round it off to 2 decimal place for this one for all? So just take the value that you have and go and square it. They just want the t squared. Okay, round off properly. So whenever it's 5 or more, you need to plus 1. No? Okay, round off like normal. I'm going to do the last two. Okay, you do the one in the for 40 cm and 50 cm again. Okay, I'm going to do the last two. This one is, oh, you did the 50 and 60 cm. This one is 1.2500, right? And then 3975. Hmm.
1.56 and 1.95.
So one thing we know now, okay, I will standardize all the decimal points. So if I use 4, then all 4. Later, I show you why we want to put 2 decimal, because in the next part on analyzing the data, to plot the graph of, they ask us to plot the graph of t against L and the graph of t squared against L on a separate sheet of graph paper. Okay, so I've shown to you how it will look like already if I draw t against L, but t squared against L will look like a straight line. Okay, so you see down there got a graph paper. What I want to do is only the t squared against L. Okay, can we try to do that? So because I want to put in the graph paper, so writing too many decimal places will be very hard to plot. Okay, that's why I just fix at 2 decimal places. Whenever we plot the values, hopefully it might be easier for the t squared. So although they say draw both, but okay, they are both actually already drawn for you. Okay, but the one that I want to get values from is this one, because this one straight line, we can do things like the gradient, the y-intercept, all those things. Okay, so let's go to the graph paper there and try to plot our values, our data. Okay, the L, right, is the length of the pendulum bob, is up to 70 cm. So when you look at your axis here, if up to 70 cm, meaning if here's 0, here's 10, 20, 30, 40, 50, 60, 70, that means up to here. Okay, this is what you need. And when you label like this one, you just have to use, we usually don't write the length of pendulum like that one. Okay, if got the symbol, we will always use the symbol. This is in CM. The next part is on the t squared. It's on the t squared. The one is in second squared. So we look at the t squared value, you will see that the values maximum is until 2.75 only. Okay, 2.75. So I see how many boxes I have. 1, 2, 3, 4, 5, 6, 7. 7 big boxes. Okay, 7 big boxes. I think we can do 0.5 for each big box. Okay. I'm gonna, so all I put 1 decimal to standardize. Okay, maximum I need until 2.75. So 3.0 is more than enough already. After fixing the scale, then we go and start to plot the points. We got length of pendulum for 20, 30, 40, 50, 60, 70. We got 6 points to plot. Okay, so when it's 20, you plot 0.77. Be very careful how you read. 2 box is equals to 0.1. Okay, just to show you, every 2 box is 0.1. So 0.77 is between 0.7 and 0.8. Okay, but it's closer to 0.8. Okay, this one is not reading value, so you don't have to. Remember, I say read value, you must get maximum. You can split the small box into half only. Okay, but this one never mind one. Plotting points is fine. Okay, you agak lah between 0.7 and 0.8, but it's closer to 0.8. And then next one is 1.23. 1.2. So 1.0, 1.1, 1.2, 2.3. Okay, 1.2 and 1.3 is here. This is 1.2, 1.3. 2.3 left would be closer to 1.2. Okay. Then the next one is 1.56. 1.5 is here. 1.6 is here. 5.6. Somewhere in the middle. Okay, you plot yourself. Okay, you draw a graph that you feel like passes through most of the points, but must pass through zero, but must pass through zero. Okay, because it makes sense if the length of the pendulum bob is zero, then of course the time also will be zero. Okay, or the time squared will also be zero. Okay, you try to find a line, adjust your ruler first after you plot the points. Make sure that you can pass through as many points as possible. Okay, as many points as possible. Hopefully can pass through at least 3. Okay, and then also you see the points balance a bit. So you draw a line of best fit. Okay, the best line that you can get. You find the values very hard to plot, I can teach you a trick. No? You can, that means that the decimal place is very hard to plot. Then you can go and round off yourself. Like let's say this 0.77. You round off to 1 decimal. Okay, make it even smaller. It'll be 0.8. Okay, 0.8. So as long as you plot very close to 0.8, but maybe slightly lower, then can already. Okay, if you find the points very hard to plot. Cannot, you need help.
Done, teacher.
Okay, and this graph a bit harder, right? Harder than just now that one. So what is the relationship between the variables in each of the graphs? Okay. Well, you can look at the 2 graphs on top here. Okay, you can look at the 2 graphs on top here. We can say that for number 1, the first graph, t increases non-linearly with L. That's the first graph. The second graph there is t squared is directly proportional, right? To L. Okay, t squared is directly proportional to L. Okay. Then we need to determine the gradient. Okay, we need to determine the gradient. Let's quickly go and find out the gradient first. Okay, let's quickly go and find out the gradient first. Maybe I can use, you can use any nice points lah. For example, like you want to use this point can, or actually you want to use this 0, 0 also can. Okay, you want to use that 0, 0 also can. And maybe a point that must be on the line. Okay, this one must be very, very, very specific because when you get the gradient, we are not looking for the gradient of the points. No, we are looking for the gradient of the line. So let's say like, for example, this point. I cannot use back the point that I did because my line, when I draw the time, it didn't pass through the point. If I want, I must go and use this coordinate, not this purple color cross. I must use the red color dot because I'm not looking for gradient of a point. I'm looking for the gradient of the line. So after you draw the line, you can kind of ignore the points already. Okay, we are going to use the line only. Okay, we're going to use the line only. So let's draw a triangle. I think I can draw a triangle. My 70, that one also passed through quite nicely. I think I am going to do a triangle like this. Okay, the biggest possible triangle. Because the two values at the ends are quite nice and it's on the line. So okay lah. This one is what, 70 and 2.75. Okay, 2.76 also can. You either use 2.75 or 2.76. Okay, 2.75 is based on my my graph I just see like that, 2.75. But 2.76 would be from the table. Okay, so you want to use 2.76 also can. 2.75 also can. Okay, since it passed through this point, okay, I use 2.76. Okay, but must make sure it passes through the line, must be on the line. Then only you can use like that. So same, I'm going to rub off a bit. Okay. My one might be different from yours. So my gradient of the t squared against L graph in SI unit would be equals to, okay, you do exactly like how I do, draw the triangle, put the 90-degree, put down the two coordinates you want to use. Okay, y value minus y value over x value minus x value. Okay, the y distance is on top, the x distance is at the bottom. You know for sure your answer will be a positive gradient also. The final answer I get 0.0394. Okay, I'll just leave it to three significant figures. 0.0394. See whether your answer is similar to mine or not. On the top part, we have the second square. At the bottom part, we got the cm. Okay, we got the cm. So it's second squared per cm. Okay, per cm. Oh, they want in SI unit though. Okay, if it's in SI unit, then maybe it's better I change to meter. Okay, then maybe it's better I change to meter. Okay, I can also write like that over cm, might be easier for me. Okay, now let's say I want to change to meter. I would need to, you see cm is at the bottom. I know that 1 meter is 100 cm. If I want to cancel the cm, I need to put 100 cm on top, 1 meter at the bottom. So the cm cancel already. End up is this value multiplied by 100, which is going to be 3.94 seconds squared per meter. Your value should be very close to mine. Anything you don't understand, you ask me first, because we will stop here today. This is the last for today. The next parts we will continue next week.
Done, teacher.
So we will stop here first today. Okay. Maybe you look back at the objective question next class at the beginning of the class. Got any questions, you ask me. Okay. Can? Or you want to ask now also can? Want to ask now? Or next week?
Teacher, I got one question already.
Oh, okay. Then you ask now. Which number is it?
26, teacher.
26. Okay. Vector quantity. The answer is what? Let me see. 26. The answer is B. Okay. Let's hope the answer or the question has nothing wrong. Vector quantity. Okay. They say the answer is B. Which one describe a vector quantity? Oh, magnitude, direction. Okay, if let's say if Dai want to take one of this, right? Do you think a base quantity, any of the 7 base quantity, are they a vector quantity or not? No, right? None of them are vector quantity. Like time, length, temperature, all also scalar quantity. All the base quantity, they are scalar quantity. Okay, all the base quantity are scalar quantity. Although it's true that not all derived quantity they are vector quantity, but some of it yes. Okay, some of it yes. So if we look at this table, I wouldn't say this question is a very good question, but if you want to pick the best answer, okay, if you want to pick the best answer, base quantity they are all scalar. Okay, base quantity they are all scalar one. So this one cannot. Okay, and we know that vector quantity must have direction and magnitude. That means number C is out. And since base is all scalar, right? So A also out, B also out. So although not all derived quantity is vector, but this is the best answer for B. Okay, derived can be scalar or vector one. Okay, but this is not a super good question because some of the derived quantities they are scalar also. Okay, and we pick the best answer.
Understand, teacher.
Okay. So can you also go and try the objective questions for this one? Next week I give you the answer. Okay, you try yourself first, the graph stuff and all. Okay, because I want to quickly wrap up chapter 1. In school, what chapter are you still in chapter 1 or are you doing chapter 2 already?
Chapter 1.
Oh, still in chapter 1. Okay, okay. All right. So we continue next week. Sorry, today delay a bit. Okay, see you. Bye-bye.
Thank you, teacher.
Welcome. Bye-bye.